So let me make some comments. So comment number one is that, U and V, the real and imaginary parts of the function f are assumed to be differential function, okay? Differentiable. Differentiable functions of x and y. Unless, but of course they can blow up in certain regions, but more or less on the two-dimensional plane, they're differentiable. So what does it mean? That we assume that, du by dx and then du by dy, dv by dx, dv by dy, these things exist, okay? So, but these things exist. But real differentiability and continuity is not the same as complex differentiability and continuity, okay? So the Cauchy-Riemann conditions are an extra condition, okay? The Cauchy-Riemann conditions are an extra set of conditions that we impose. And this has a geometric significance. And I won't give you an example now because I can't recall it exactly, off the top of my head, but you can show that there are functions, for example. So if I have, say, a two-dimensional complex plane, and this is the real axis, and this is the imaginary axis, there are functions such that, if you approach some point, say along the x-axis, so suppose that this is some point, the red point, and you're approaching it along the x-axis, it's differentiable. And if you approach it along, say, the y-axis, it is also differentiable. But if you approach it, from some other direction, then it's not differentiable, okay? So such functions can be cooked up very easily. However, if you impose that your functions, in addition to be different, also satisfy the Cauchy-Riemann condition at some point, then it doesn't matter which path you take, the function will be differentiable, okay? You can approach it in any direction and it'll be differentiable there, okay? So in some sense, the Cauchy-Riemann condition makes the whole thing coordinate invariant, okay? Right, so, Cauchy, imposing meaning that it doesn't matter which coordinate you use, which direction you use to approach that point, it is differentiable, okay? So in other way, unless you impose a Cauchy-Riemann condition, the real part of your function and the imaginary part of your function don't really unify to form something whole, okay? They remain sort of separate. And as you can see, the Cauchy-Riemann condition conditions, they connect the real and imaginary part and how their continuity properties are related. Okay, and therefore it gives rise to holomorphic functions. Okay, so that's comment number one. Comment number two is that suppose you have a analytic or a holomorphic function f of z. This is a holomorphic function. Then it's very easy to create new holomorphic functions out of it. In fact, you can create an infinite number of holomorphic functions, okay, if you are given a holomorphic function. And how do you do that? Note that if you define f of z to be, say, w, then any function of w, so this is a complex number, right? Which is g of f of w. This is a holomorphic function of w, right? Because if I take the derivative of g with respect to w bar, it's 0 by definition. So it's very easy to create holomorphic functions if you're given one.
Sir, on the right side of the equation, f of z, wouldn't it be f of z or w? G of f. Okay.
Thank you. Yeah. So for example, let me give you some examples of holomorphic function. Z is a holomorphic function. 1 over z is a holomorphic function, but this has a singularity at 0. This has a singularity at infinity. 1 over z cubed, e to the power z, sine of z. These are all holomorphic functions. But 1 over z star, which I can write as z, this is not holomorphic because it depends on z bar. Okay? So for example, if I take a complex number and take its modulus, this is not holomorphic, whereas this is. So this is a very simple holomorphic function, just the complex. Then we can say, okay, let's define g of z to be, say, z cubed. Well, this is a new holomorphic function. And let's say cosine of, say, g. Well, what is cosine of g? It is cosine of z cubed. And of course, this is also a holomorphic function. So whenever you do this, whenever you take a holomorphic function of a holomorphic function, what are you doing? You are mapping the complex plane onto itself, right? And these mappings preserve angles between curves. They don't preserve the length, but they preserve the angles between curves, except at some, special points. And hang on. And these maps are called conformal maps. Okay, conformal maps. And complex analysis is very useful for two-dimensional, a kind of two-dimensional quantum field theory, conformal field theory, which is used widely in string theory and two-dimensional condensed matter systems. Okay, so those are my comments on holomorphic functions. So any function that you can cook up, a function of z, is automatically holomorphic. So there are essentially an infinite number of holomorphic functions, right? Okay, any questions?
The CFT correspondence, does it work on 2D space?
What you mean ADS-CFT?
Yes.
Yeah, it works on a wide range of theories. It's actually easier to work in lower dimensions.
Oh, okay.
Okay, so our next topic is our contour integrals, okay? So I'm especially interested in questions from people who have not seen complex analysis before, okay? So people like Saif or Shujosh, I am especially interested in getting your feedback on this lecture, okay?
Yeah, I've been unusually bad at coming up with questions this class.
No, but you
Same.
don't have to come up with questions. You just like follow along, and if you cannot follow something, stop me and ask me questions or ask me to explain something again. And that's how I want this to work, okay?
Yeah, so far I'm keeping up with it.
Okay. Shujosh?
Yeah.
Okay, good. Don't be shy, okay?
Okay.
Yeah.
All right. So our next topic is contour integrals. So what is like a holomorphic function? So we have a complex plane. So this is my representation of a plane. And this is my original complex plane. So, sorry. And I have another complex plane, which is the function. Is that we have a function which is also a complex number, right? So this is where my original complex plane is, and this is Z. And this is another complex plane, but here the variable is f of Z, right? So when we are talking about a holomorphic function, we are looking at maps, from this plane, from one complex plane to another, right? So